So tonight we have two speakers for you. The first topic will be on Jellyfish Galaxies, and the second talk will be on the IGM. So we'll have both speakers tell you more about that. Thank you all for coming on this rainy evening. All I would like to ask is that if you're not here for astronomy on tap, that you respect the speakers and try to keep your noise level down so that we can hear the speakers talking. So let me get the bio up for our first speaker. All right, so our first speaker is Anitha Shaji. She is a PhD student at the Lerma Laboratory at the Observatory and the Sorbonne University. She is currently working on links between gas morphokinematics and feedback processes in nearby galaxies. So today she'll be talking about the fascinating world of jellyfish galaxies, exploring their formation and the crucial role of their environmental interactions through observational studies and theoretical models. So please let's thank our speaker. Thank you.
Hello, good evening to everybody. Can you hear me? Okay, perfect. Thank you so much for that kind introduction, and I'm so excited to have this opportunity to speak with you all today on one of my most favorite topics in galactic astrophysics, that is jellyfish galaxies. I have to make a small confession before I start. One is that I don't directly work on jellyfish galaxies. Two, to the telesophiles in the audience who thought we'll be discussing about oceans and jellyfishes, we may have been slightly clickbaited, but I promise you that what I'm going to show you today is equally, if not more, fascinating. Alright, so for the next 3 minutes or so, I want all of you to assume that you are observational astronomers and carefully inspect 5 galaxy images that I'm going to show you. Is that a deal? Alright? That's image 1. Image 2. Image 3. Image 4. And image 5. So, do you see anything in common in all of these 5 pictures? Yes, no, maybe, no? Alright, so, ooh, yeah, exactly. So, in case you want to see the pictures again, they're all here together. And yes, you're right, they all have these little tail-like structures, which I like to fancily call tentacles. And as you can see, all of them have tentacles, some long, some short, some continuous, some discontinuous. And I know you have too many questions now, like how are they formed, why do they have tails, what do the tails do to the galaxies, right? So I tried to talk about these in mainly 3 sections: how were they discovered, and secondly, how are they formed, and why do we study them. So about the first part of discovery, I'm gonna go take you back all to your high school physics. I hope you remember this electromagnetic spectrum. Yeah, at some point I had to bite heart and I hated it, but yeah. There's a good news and bad news, okay? So the bad news is that when you look at the universe through each of these wavelengths, you see a different thing. You see very different things because they trace different things, they probe different things, okay? So, but the good news is that all of these so the good news is that all of these, we have a telescope for all of these wavelength regimes, right? So what I've put here is very few, but there are much more telescopes and observatories on space, on land, single dishes, many arrays, but they're all there and they're all looking at the universe one part at a time, one wavelength at a time. Alright, so what observational astronomers do is they combine all of these images or information from different wavelengths and they study it together to see if there is a cohesive physical phenomena explaining different things, right? Alright, so the jellyfish galaxies that I showed you were very pretty, but when they were first studied, it looked something like this, which isn't that pretty, right? But here all we see is that we see like a superposition of stars and UV light. So if there is white blotches, they are stars. If there are black blotches, they are not stars. And the gray lines that you see is basically starlight. So that means there's something there that we don't see in the physical, but they're there, right? So I'd like you to remember three things before we proceed further. That, for example, the X-ray regime, it traces really hot gas, and one of the best instruments tracing X-ray is called Chandra. Then the visible part of the spectrum, they trace stars, and two of the best instruments tracing them are Hubble and JWST. You must have seen that most of the 5 pictures that I showed before were taken by Hubble. And finally, when we talk about these radio and microwave, we call them millimeter data because their wavelengths are too tiny. And they trace cold and dense gas. And the best telescope or observatory for that is ALMA. ALMA has detected more than 200 species, 200 molecules in different parts of the sky in the universe. So with that information, we can now look at how these jellyfish galaxies formed, right? The easiest answer to the question is galaxy clusters. So galaxy clusters are these largest structures of the universe held together by their own gravity, and they contain or they consist of almost hundreds or sometimes even thousands of galaxies, lots and lots of hot plasma, and also a large amount of invisible dark matter. So this picture that you see here is particularly is called the coma cluster, and this particular galaxy has more than 1,000 identified members. So the idea is that when a galaxy falls into the cluster, although it's not as simple as this is, like this particular animation that I use, it's more complicated because it's usually goes around and around in spirals and probably takes years and years, not 3 seconds, probably takes billions and millions of years. And the idea is that when one such galaxy falls into a big cluster like this, it faces something called a ramp pressure stripping, okay? So this is a physical phenomenon that was first coined by these two researchers called Gunn and Gott in 1972. That's so long ago. And then, what is this, right? Ramp pressure stripping. So basically, ramp pressure is the pressure or force by unit area faced when a body moves through a fluid. So what is the fluid in our case? The fluid is basically the hot plasma that I talked to you about that is already there in the cluster, which astronomers astronomers like to call intracluster gas. And for the nerds in the room, I put one equation. The pressure is equal to rho. Rho is the density of the intracluster gas, and it's proportional to the square of the velocity or square of the speed with which the galaxy falls into the cluster. So like a very intuitive way of thinking about it is if you are sitting on a motorbike and you ride it very, very quickly or very, very fast, all the loosely attached items on your body is going to fly away. Like your hair is going to fly away, your muffler is probably going to fly away. So that's the idea. So it's very similar. And more things are going to fly away if you ride faster. And the wind that is blowing on your face, that's the intracluster gas. And if there's more wind, obviously more things are also going to fly away from your body, right? Another example that I really like is if you put a bag of flour on a dog's head and make him sit in a car, and if the doggo puts his head outside the window, all of the flour is going to fly away. So that's exactly what's happening in Jellyfish Galaxies, okay? This is one of my favorite Jellyfish Galaxy. So it's called ESO 137001. Weird name, astronomers don't know how to name things. But it is falling onto Norma cluster. And right now what we're seeing here is just one image. It's just one telescope. That is the Hubble Space Telescope. So basically we're probing the optical area, around the optical area, and what we see here is stars. Now, if you add Chandra, which was the X-ray probing telescope, you start seeing more things at the edge, right? So that's Chandra, and the rest is already interesting. Now, if you use other telescopes like Alpha and Muse, Alpha is the molecule detecting telescope, and Muse is, for now I'm going to say, something that traces H alpha, and H alpha, or just starlight, something that traces starlight. And then, basically what we see is that stars are forming even at the edge, in the tails, that has been stripped away, okay? So wherever there is molecular star, like red regions, they are called places of CO. We see a lot of carbon monoxide in that region, and if there is carbon monoxide, it means stars will start forming very soon. So if you compare the rates at which stars are formed in the tails and in the galaxies, they're almost similar, very similar, and that's very surprising to a lot of astrophysicists. However, okay, this is not supposed to be here. Okay, so finally, now why do we need to study such jellyfish galaxies, right? So in the general theory of galaxy evolution, galaxies like evolve from young, blue, star-forming spiral galaxies, like ones on the left here, to old, red, non-star-forming elliptical galaxies, like boring shapes, and they happen because they stopped forming stars. And the process by which they stop forming stars is a process called quenching. Alright, this is the general theory of galaxy evolution. So if you put all the galaxies that we know, their masses, the colors of the galaxies and the masses, we see that there is a bimodal distribution, basically a peak here, and something in between. You put that on a histogram, you get like this. So there's a peak of very old quenched galaxies, and there is a peak of star-forming galaxies, and in the middle there is a valley, but there are still stars, there are still galaxies, and they're called the Green Valley galaxies, alright? So they are not, they're basically, their star formation has reduced, like the star formation rate is reduced in these galaxies. So this is, they evolved from blue star forming to red non-star forming, and these are the galaxies in between. And what astronomers believe is that jellyfish galaxies is what explains such quenching mechanisms. So basically, if the gas of the galaxy is taken away, you don't have any more material to form stars inside the galaxies, right? So that's the idea. And another detection we know is that at the center of the clusters that I talked to you about, the galaxy clusters, which has so many galaxies, most of them are quenched galaxies. So this sort of helps, because if a galaxy that's falling into the cluster experiences ramp pressure stripping, it is going to lose all of its gas from the disk and end up becoming an old, boring, non-star forming galaxy. That's the idea. But some other researchers say that if it were true, then we'd see like millions and millions of galaxies, jellyfish galaxies. But here in this picture, all the dots, all the crosses, all the triangles, they are galaxies belonging to this one cluster, Chroma cluster, and only the ones with the tail here, the black little lines, are jellyfish galaxies, or they're the only ones experiencing ramp pressure stripping. So if it were a common phenomena, you would see much more galaxies experiencing it, but since you see only like 10 in thousands of galaxies, maybe that's not the only case that experience, only reason that explains quenching in galaxies is the second importance of this. And lastly, this is a Nature paper, and this is the best explanation of jellyfish galaxies, is that supermassive black holes, basically things in the center of the galaxy, they're very hungry for more gas, and if jellyfish galaxies can drive more gas into the center of the galaxy, thereby feeding the supermassive black hole. This sounds a bit weird, because in one sense you're pulling gas away due to ramp pressure stripping, but in another sense you're saying, oh, you're feeding the supermassive black hole. That doesn't make sense. Here there is a little thing that comes into play. It's basically something called angular momentum. So when you're stripping gas away, the angular momentum decreases, and the gas that's already existing in the galaxy may fall more into the central areas, thereby feeding supermassive black holes. So these are the two main results that have been published and agreed upon, but we have so many more questions yet to be answered, such as what are the timescales of all of these processes, right? Like how long will it take for the gas to completely taken away from the galaxy, and how long does it take for stars to start forming in these stripped tails? So there's a lot of question about timescales. Then there's also a question about survival of these dense clouds in the tails itself. So the tails are very high pressure region. So should these molecular clouds or dense clouds survive? Yes or no? Question, we don't know. Still trying to answer. Magnetic fields in these tails, because whenever there are stars, we know there are magnetic fields. So there's a lot of studies coming up on magnetic field and much more. So with that, I end with one joke or a question for all of you. Why did the galaxy laugh? Yeah, well, I didn't know either until someone pointed out to me, who said, because it's got tentacles. Alright, with that, if you have any more questions, you're free to ask. I'm most happy to answer, and you can also send me an email, and I hope you like the talk. I hope you
Okay, so now we'll have a time for question and answer. If you have a question, please raise your hand. We'll bring you the microphone, and you can ask your question. I'll bring it.
you have a theory on why they are scattered around and none of them are close to each
Actually, if you look at the X on the graph, we're looking at the 0.2 arc-second difference. So basically, we've zoomed it into a particular area, but it's still quite close by. Like, you see what I mean? Like, it's 0.2 in our field of view, but then when it's far away, they all have the same. They're all pushed. They're all bound together by the same gravitational forces. However, it just seems scattered in this particular image because we just made it bigger, or people who made this just made it bigger so that the tails can be visible. But in reality, they're much closer than you expect. It's not this scattered. It's just the illusion of scatter.
Really interesting talk. Thank you. Have you seen anything, or have we learned anything about the overall direction of the tail? So I would naively imagine that they would always be pointing away from sort of center cluster, but I don't know. Could you learn more about the overall orientation of the satellites in the cluster or something like that?
Yeah, well, you're right. Like most of the times, if they are falling, for example, in this picture itself, the center of the cluster is somewhere here, right? And this particular galaxy is depending on the direction in which it's moving as well. So for example, here it's maybe by this tail, we can see that it's moving in this direction, yeah? And that's why the tail is pointing behind it, sort of thing. So it will mostly depend upon the direction in which the galaxies are moving. And yeah, naively, it's true. And it's not a naive idea, it's a very true thing, and that's exactly how it would work. And also, it is also possible that some of these clusters, the hot plasma that I was talking to you about, they could be doing their own dance. You see, so sometimes they might be, it can so happen that two clusters can fall into each other. So the winds of the two different clusters, they can be swashing around like a wave on the beach. So it will also depend upon that plasma, the direction of the plasma, direction of the galaxy's movement. Yeah.
Any other questions?
Let's say the proportion of these galaxies when you see the tail, can you describe information about the proportion of these galaxies that they are falling into the clusters?
Yes, actually using spectroscopic studies, I think you can do that because we know one of these galaxies will be so. Sorry, I keep forgetting to find that. Yeah, this one. I think this is falling at a rate of 7.2 million kilometers per hour. My memory is right, it's something around this. So, it is quite difficult to do that, but I'm sure it can be done.
Thank you so much for your talk. It was very interesting. I wanted to ask you, so you explained that the two theories are that one, the jellyfish galaxies are the cause of quenching, and two, that they
jellyfish galaxies help feed the supermassive black holes.
Okay, and are these two theories contradictory? Or
Tiny bit, yes. No, not necessarily. Actually, I think it can happen together as well. Because in a particular galaxy that I'm studying for my PhD, what's happening is that it's a group of galaxies. There are 3 galaxies. They're merging with each other. They're falling onto a cluster, and 2 of them have supermassive black. Like honestly, all galaxies have supermassive black hole. And when I say supermassive black holes are feeding, I mean they're active. That means they're eating a lot of gas basically, and they're burping out a lot of gas as well. So 2 of the galaxies of the group are EGNs. So EGNs are feeding supermassive black holes. So it can so happen that all of these processes can happen simultaneously. So when it's falling on the gas, the wind can blow away, so that can cause the jellyfish-like tails. And inside, because of the angular momentum reduction, there can be more gas that's funneling into the center of the galaxy, thereby feeding the supermassive black holes. So not necessarily, it sounds like contradictory ideas, but then they can coexist is my point.
so it's about the supermassive black hole in the center of the galaxy, which is the jellyfish galaxy itself, and not in the center of the cluster? Or
Could you repeat that? I'm sorry.
so it's about a supermassive black hole which is in the center of the galaxy, and not in the center of the cluster.
Yeah, that's exactly. It's about what happens to that particular galaxy that's undergoing ramp pressure stripping. So it's in the center of that galaxy, not in the center of the cluster. There is no supermassive black hole in the center of the cluster. Well, possibly not.
I think we have time for one more question. If someone else has a question. Okay, well, let's thank our speaker again.
Thank you so much.
All right, so now we'll have about a 15-minute break. You can go and get another beer, and we'll take the next set of slides.